All right, guys, welcome back. And now we are finally going to jump into our first unit, which is functions. And I know we hit it a little bit, but we're just going to go over it again. And I'm going to make sure to hit different points now that we're in Delta Math um, to match things that are in Delta Math. So my think/follow is think about your science classes. When you made a graph about data, which axis, X or Y, did you make your independent variable, which is your input, and your dependent variable, which is your output, right? So typically, if you graph something on your just X and Y axis, your independent variable would be on X, your independent variable, and your dependent variable would be your Y. And so that's also known as input and output. So X is usually your input and Y is usually your output, right? When you're measuring something, let's say you're comparing height and weight, right? You're saying the taller someone is, so the further down this x-axis, or you're saying you can determine someone's average weight by their height. So let's say they're this tall on the x-axis. You're saying if I input this height, that means that they're probably around that weight, right? And so a relationship, to get more into functions, I just kind of wanted to introduce you to the idea of input and output, and X being the input and Y being the output. And we think about that when we see like a table too, right? X is usually our input and Y is our output. And so the definition of a function is a relationship between inputs and outputs is a function if there is exactly one output for each input. And that's really important right here. Exactly one output for each input. And we'll see some examples that'll make that clear as well. And then functions are usually written as y equals some expression of x. You guys have seen a million of these. So for an example, the following equations, table, and graph are representations of the same function. So this y equals x minus 2 squared is the equation, right? And that's a function. And then this table here, that is the table. And then we have the graph over here, and that is the graph. And all three of these represent the same function, right? This is the algebraic equation right here, but if we were to plug in x equals 0, notice on our graph, x equals 0, that'd be negative 2 in parentheses squared. Negative 2 times negative 2 is positive 4. It gives us our y, right? So all of these forms are saying the same thing, right? And then if we were to plug in 0 for x, 0 on x is right here, right? Because this is x and this is y. And then if we went up, that looks like it's at about 4, right? So that just kind of goes to show that every one of these three things is the same thing, just shown differently, right? This is shown algebraically, and this is shown point by point in a table. But if we were to list out every single point, that'd be the same thing as that equation. And then this graph is just this table, but with every single point, right? We have 0 and 4, we have 1 and 1, and we have 2 and 0. But if we were to get every little thing in between there, that's what that graph would be. So for our first example, do the following mappings represent a function y or y not? And remember, our golden rule is for each input, we need only one output. And so here we're talking about sets, and sometimes sets kind of have this bracket notation, and then you put numbers in them. But here we're just kind of representing them by a circle. And I know everyone gets confused by what a set is in math. And the way I like to describe a set in math is like a box, right? This box has nothing in it. Now this box has a marker in it, right? And that's kind of what a set is. A set is just like a box that we put numbers in. So this set, we have -1 going to -2, and then we have -2 going to -2 and 3, and right away we have, this is our input, right? This is our input, this is our set, and this is our output, right? So these are numbers getting mapped or sent to a different number in a different set. So here we have a single input going to multiple outputs, right? But we just set up here that it can only go to one output. So this is not a function. And it's because this 2 is going to multiple things, different things. Now looking at this one, well, if we look at this one, each input only has a single output. We notice how each of those things only go to one thing over here. It's 1 to 1. So this is a function. Because we don't, unlike here, we don't have a single input getting sent to multiple outputs. Now here's one that might throw some people off. Take a second to think about this one and what you think. Is this a function, yes or no? And I encourage you to pause and think about it a little bit before I explain it. But the answer essentially is this is a function, right? Because what might be throwing people off is right here we have two things going to the same output. But isn't that within our rule? Let's take a look at our rule again. Our rule is for each input, there's only one output. Well, this is an input that only has one output. This is an input that only has one output. And this is an input that only has one output. It doesn't matter that we didn't touch this 1, and it doesn't matter that two things got sent to 9. All that matters is that each individual input only got sent to one thing as an output. So that is a function. And now for example 2, we're going to deal with sets, except we're going to deal with sets of ordered pairs. And this is probably more how you're used to seeing sets with these squiggly lines. And just a refresher on an ordered pair just means X and Y value typically, right? So we could think of that as X and Y, input, output, output for each one, right? So what I'm going to be looking for is if there are two inputs, so two values of X that produce a different output Y. So we have 4 and 6, we have 9 and 2, 3 and 6. Well, we don't even have multiple of the same inputs, so we're good. Here we have -1 and -4, 8 and 1, all different inputs, so there's no possibility of having the same input go to multiple things. -1, -7, 3 and 4. Again, all different inputs, so we don't have the same input going to multiple things. 2, 0, 2, -3. Ooh, here's a discrepancy, right? We have two of the same input, but this one is getting sent to the output 2, and this one is getting sent to our Y output of 7, right? So here's an input paired with an output 2, and the same input paired with an output 7. So same input, different outputs. So this is the one that is not a function. And now let's think about it graphically. Do the following graphs represent a function, y or y not? And again, let's just think about what we have here. X is our input, right? And Y is our output. So for every single input, X, we can only have one output. So we don't have any outputs, we don't have any outputs until we get to here. Well, our output here is -2 on the y, right? So that one's good. But then notice as soon as we go over anywhere else, let's say here, don't we have 2 outputs? And that's a problem, right? So this is not a function. Right? For one input x, we have an output there and an output there. That's 2 outputs for the same input, so it's not a function. And a good way to look at this is if you make a line, and this is called the vertical line test, and you just imagine a vertical line going across. If at any point this vertical line crosses 2 times, like it does right here, and like it does anywhere here, right? All of these times it's crossing more than once, then it's not a function, right? And why is because when you do that, you have one input for 2 outputs. That's what that line is testing. So let's go down to this one, and visually in my head, I'm going to make this line, but luckily I can make it just like that. And I'm just going to scan this across. Now, at any point, is this line hitting more than once on the graph? It might look a little weird, like here. You might say, oh, that's kind of multiple. But once you think about it, if we were to pick an exact point, it would really only have a single point, right? So this actually is a function. And that's going to end it for our definition of a function and determining if different representations are functions or not.